Let's talk, but let's not talk too long about Newton's laws of motion. This is Sir Isaac Newton with the aspect ratio slightly altered. Um, he is an interesting character. So if you ever have to do a little bio on somebody, Sir Isaac Newton is pretty fascinating. Anyway, these are the three laws. There's 1, 2, and 3, right? And the first one is that an object at rest will remain at rest. An object in motion will remain in motion at a constant speed in a straight line unless acted upon by an outside force. Okay? Um, and basically what this says, and this is just nothing new, right, beyond Galileo, is that objects have inertia. They have a tendency to resist a change in their motion. And when we say motion, we are talking about the velocity, okay? So if you go into outer space and there's no outside forces acting on some object, and you throw a baseball into space, it's going to go in a perfectly laser straight line. It's going to move at exactly the same speed. If you looked at it every second, it would move exactly the same distance every second. If it had a rotation about it, right, that rotation would remain oriented toward exactly the same direction in space. It would be exactly the same revolutions per minute that it ever started out with. The notion here is that objects' motion isn't what forces cause. Forces cause change in that motion, okay? That objects just, if there is no force, there is no change in the motion. So then this is sort of a radical concept. You have to have the concept of inertia to believe that the Earth, for example, rotates once, if we look down at the North Pole, right? The Earth rotates once every 24 hours, because that means that the equator is going something like 1,000 miles per hour, right? And the reason that it can do that is that, of course, it has inertia. The air at the equator, the trees, the water, everything is moving at the same speed, and it keeps moving because of inertia, which is, around Galileo's time that was in play, right? Is the Earth moving and the heavens are still, or is I'm going off on a tangent here, right? Is the Earth moving and the heavens are still, or are the heavens moving around the Earth and the Earth is sitting still, right? This is the eternal question, right? I think we know the answer to that one, right? And then the next law looks suspiciously like a formula, and of course we're going to do a lot of our calculations here, right? Is that if there is an outside force, right? So this is unless acted upon by an outside force, right? So what if there is an outside force? Well, if there is an outside force, this is it, right? You add up all the forces that are acting on it. So this is the net force. Okay, so if we have, for example, a force this way of 10 and a force this way of 3, and those are the only two forces, then we have a net force of 7 to the right, 7 newtons maybe, right? Okay, if you add up all the outside forces and they add up to something other than 0, then there must be an acceleration, and that acceleration is proportional to the force and inversely proportional to the mass, right? So more massive objects are hard to accelerate. Bigger forces cause bigger accelerations, right? All right. Yeah, that's kind of cool. F equals ma, baby. It's a way of life. And then the final one is for every action, there's an equal and opposite reaction. Now, mind you, we don't know why these laws are the way they are. They make the universe make sense, or maybe it makes sense because that's all we've ever seen is the universe. But this is what the third one says, right? Is that let's imagine that I've got a perfectly frictionless sheet of ice, and I'm standing here on ice skates. Picture my ice skates, right? And imagine that I throw a ball this way. I'm sitting in rest initially, right? Imagine that I throw a ball this way. What Newton's third law says is that if I'm standing on these frictionless ice skates and I throw a ball this way, there's no way for me to do it that I don't go backwards, I don't recoil. Well, unless, of course, it is to throw a ball in both directions at the same speed with the same mass, right? Okay, but if all I do is I throw one ball and I throw it this way, there's no way that I can do it that I don't recoil backwards, right? And even if I don't have the ice skates and frictionless surface here, even if I'm standing on the Earth, okay, if I throw it this way, the Earth and I go back this way, right? It's just that the Earth is kind of big, right? So I think it moves like one atomic diameter in a millennium or something like that. Okay, it's not very fast. Of course, this explains why if we fire a rifle or shotgun or something like that, the bullet goes this way, right, and the gun goes this way, right? This is the kick in the gun. This is how rockets work in space, right? In space, there's nothing to push off of, right? Okay, so the rocket ship shoots molecules this way, and the molecules push the rocket ship that way. Okay? These equal and opposite reaction forces act on different objects. They're always the same kind of force, too. Okay, so like, for example, this is a contact force. That's a contact force. If it's a force of gravity, they're both gravity forces, for example. Okay? Those are the three laws, and thank you for listening.